So the first step in cleaning this up is, well, after I made a copy, I went through with the find and replace dialog boxes and adjusted all the names to get some better names going on in here. So everything's still the same. I just changed all the names to something a little more meaningful. And I wanted to clear up a couple points here that weren't stated explicitly earlier, such as this, where I was using a long to return this. And if you've dealt with this sort of thing before, you might be asking, well, don't we usually do that in hex code? And yes, we do. But remember, hex code is working in binary. If we're looking at hex, we're working in binary 4 bits at a time. And the binary for a signed long integer is exactly the same as the hex representation would give us. So the only difference between calling that a long or what is in C++, u int underscore 8 and get the hex code, the only difference is in the print statement. And personally, I find it a little bit easier to work with the long. And if we do decide to change that to hex later, we can just go to the find and replace box and then change those longs to so that it prints out in the hex code. But remember, the binary is exactly the same. The only difference between calling it a long or specifically putting a type that will print out the hex code is in the print method, not in the data itself. So I wanted to cover that. And the next thing I'm going to do is this much of the protocol will work. So I'm going to move this over to the C++, which means if we're doing it in that file, we won't need the pointers. And well, the difference between that, a little bit more on that memory management thing. You might be wondering, well, why didn't you do that? Go ahead and set that up as a reference instead of a pointer. And the biggest difference is doing that with what you might be used to in C++ has to do with memory management. And if that's what you're thinking, you're probably used to doing things on like the PC here, where we likely have parallel processors running lots of multi-threaded programs at once. So we need to do lots of memory cleanup. But here we are making a single function device. So it's a single function device. It only does one thing. So when we run this, we just want to throw that object on the heap and then keep that object on the heap until we disconnect power. So we don't really need the memory management here. So I like to use just keep stuff in the heap instead of bringing references over to the stack, and only bring pointers over to the stack for single purpose devices. I've never sat down with a calculator to see if it does much difference, but something internally there made more sense in my mind at one point in the past. And that's the reason I like to use pointers on these single purpose devices, because we don't need to manage the memory. We're going to throw it in the heap and we're going to leave it there until we disconnect the power, because there's only one purpose for this device. We don't need to clean it up so that another program can use that memory. Just in case anybody was wondering why I was using the pointers instead of the references, the arrow instead of the dot. But I'm going to move this protocol over to the C++ one and then give this another test, and then I will add in those other things and we'll come back and look at the other stuff. But it's just going to be a copy and paste just with some useful names. But now there's useful names in C++, and we've already seen all that, so there's no need to watch me type it again. It'll be the same thing, and then we'll just scroll through and look at the code quickly afterwards. But at this point, just better made a copy of the library as it was, and then went through and changed all the names to something more useful. And yeah, and that was just Control H to get the find and replace dialog box, or Control H here and Control F here. But the find and replace dialog box, and gave some better names, even in the keywords, so it'll change colors and stuff. So now I'm going to copy the protocol over to the C++, which is just going to be copy and paste, and then take out, since it'll be in its own code, we won't need to refer to the object. We can just call the method. So then take out those. And then that way, everything about the controller will be encapsulated here, so that in our loop, we'll just say, well, if there's something on the serial line, grab that thing, and then we'll have like, I don't know, controller dot respond, or controller arrow respond, I guess. But then we'll just call one method that does all this, because that is part of the controller, so that needs to be in the virtual version of the controller. So I'll get that cleaned up, and we'll come back and take a quick look at that thing. Okay, so I got that moved over, and you can see the code here is a whole lot shorter. I think we now have more comments than actual code here, but all we do is initialize our controller and the serial port, which I could probably go ahead and initialize the serial port from the controller, because, well, it needs to be here. Never mind. So we initialize the serial port and our controller, and then in the loop, we just check if there's something coming down the serial port. If there is, we grab it and pass it to this method called respond. So over in the C++, set up the respond method, and I also copied over the Doxygen comments, because those go with this method now, and it'll look better from the C++ file in the result of the Doxygen as well. So I got that over here, threw it in the keywords, and then it's an exact copy of what was there. It takes in a string called PC command. Oh, which this might be important to note. Notice I said string, and it recognized that, but I did not import the standard, the STD, the standard input-output stuff. So that's an Arduino string, not a C++ string. Because if you haven't encountered that before, the two are not compatible. The standard STD namespace in C++ is not compatible with an Arduino string. So I just went ahead and used an Arduino string over here. Then otherwise just copied it over, and again hit Control H to change all of the things that said controller to this. Seemed a quick way to get that adjusted. It's optional in this case, but it seemed quicker just to do that on Control H and change them all at once. And otherwise it's exactly like it was, and the test returned the same results. So now ready to expand this and add in the new stuff, which again is going to be more copy and paste, because the new stuff isn't necessarily doing different things. Buttons and flip switches are about the same thing, so a useful name for it. And we have two potentiometers here, and the knob and the slider are both potentiometers, and each one of our joysticks set up has two potentiometers, and then the other thing was another joystick, which will be an exact copy of this. So some copy and pasting to get the other stuff in, and I'll be back in just a second to look at that. All right, so I just finished updating the C++ library. I ran the last test. It wasn't bad, all copy and paste, but I did go kind of slow and was slow and careful with it, make sure everything went in there. And you can see here I did end up going back to just printing the hex value, because here if we ask for the total command, the total state of the controller, you can see looking at the hex here, that's definitely more than 64 bits long. So even a long integer wouldn't work. So I had to go back to that, but this is still the same. There's more pins in the constructor that need passed in, but in the loop, well, all we do is initialize the serial port, initialize the controller, and then the loop, if something comes down the serial comm line, we'll grab whatever's there and pass it to this respond method. So that's all the Arduino's doing. There's not much going on in the Arduino, and I like to put everything on the C++. There are a couple advantages to doing that, but I think mostly it's just an organization thing that makes sense in my mind. There's a virtual version of the controller, and everything about the controller is in that virtual version. So if we come over here and look at the C++, that's error message a long way. Well, start with valid commands. So added a U-axis and V-axis to valid commands, along with a flip, slide, a flip, slide, and twist command in the thing. And as we already saw, the sliding potentiometers have two outputs. I only used one of them because they give the same value. So I just went ahead and only used one of them. So then, yeah, in the header file, everything with the comments and the variables and everything just declared over here. I did go ahead and do a commented out declaration on that other one in case I want to come back to it, but only using one for right now. You can see a lot of copy and paste things that were already there. Oh, I have to update the doxygen. I still have to do the parameters here, and I think the rest of them are good. So I'll update that still. And then over here, well, the constructor got a lot bigger because there's a lot more things connected to it, but it's still doing the same thing. Just takes in whatever integer we send it and assigns that into this variable. And then in the initialization, use the pin mode set to input to kind of turn those integers into pins. And then just still getters and setters are about the same. The flip switch is a digital, and the twisting knob and slider, those go from 0 to 100, just as far as twisted all the way to the left is 0, all the way to the right is 100. And same thing with the slider, all the way to the left is, slide it to the left is 0, slide it to the right is 100. Get a % of the way. And then, yeah, added just the basic return on those. And for these combined ones, well, a 64-bit integer wasn't going to be enough. So it's still kind of the same. We have a long, was this the movement? Just added a second axis in there, and could have done a 64-bit unsigned long, but I just kept 32-bit longs and did one for the XY, one for the UV axis, and then changed it at the print. Then I'll just did the print method and print it out in hex. Print out the XY one, print out the UV one is hex, and then the line break. And for the action, I put the twist and slider here, so those each take up a byte. Kind of the same thing, just put the value of the twist knob in there, shift it over 8 bits to get room for the slider, shuffle that over 5 bits to bring in the next 5 controls, which the flip switch is then the last one. So there's 5 bits here instead of 4, but it still fits nicely in one byte. And kind of the same thing here, save those all. Each section is longs, put all that, shuffled the bits around to the right positions, and then just print them out and print out the hex values for each one right next to each other. You can see it kind of fit. Let's see, what can I do? Well, I'll call total again. So if I bring up the total state, then we have two hex values, so 4 bits in each hex, so 8 bits for the X, 8 bits for the Y, it's not selected, 8 bits for the U, 8 bits for the V axis, 8 bits for the twister, 8 bits for the slider, and 8 bits for the buttons and switches. So everything's working out here, and it's all updated. So now we're ready to get into writing some stuff on the computer that will ask for those values and then do things when they come back. But a little bit more than is needed for this current project, as was already mentioned, but now there's a lot more expansion room, and we can combine these controls with our logical operators, do the ands, ors, and nots, and get lots and lots of power from the combination of these controls. So we're ready to write a script that'll run on the computer and receive these. So I think I'm going to start with replacing mouse controls. I think that'll be a little bit easier, and then we'll go in and do and set it up as a game controller, because I figure the mouse will be easier to start with, because to do the game controller thing, we're going to have to program a game to test with. So let's get started on that now.